Have you ever stopped to think about what connects something like the sweet smell of vanilla, the warmth of cinnamon, and weirdly enough, the sharp smell of nail polish remover? I mean, it sounds random, right? But the answer is this really cool piece of chemistry that's basically hiding in plain sight. I mean, seriously. On the surface, they couldn't be more different. You've got a flavor from a bean, a spice from tree bark, and then a really powerful industrial solvent. So what in the world is the chemical thread that ties all of these things together? Well, believe it or not, the secret link between vanilla, cinnamon, solvents, and even something like the first plastics, it's not some crazy complex formula. It's actually an incredibly common and really powerful little chemical structure. Just a single group of atoms that's responsible for giving all these things their unique properties. And that brings us to the hero of our story today, the carbonyl group. This is the little chemical building block that we're going to dive into. So what is a carbonyl group? It sounds complicated, but it's not. It's just one carbon atom double bonded to one oxygen atom. That's literally it. C, double bond O. This super simple arrangement is the core of a massive family of compounds, including the aldehydes, ketones, and acids we're about to get into. And the real secret to the carbonyl's power? It's all about polarity. You see, oxygen is what we call more electronegative than carbon. It's kind of like an electron hog. It pulls those shared electrons in the double bond closer to itself. What does that do? Well, it gives the oxygen a slight negative charge and leaves the poor carbon with a slight positive charge. And that little imbalance, that's everything. It makes that carbon atom a perfect target for all sorts of chemical reactions. Okay, so because it's so reactive, this leads us to the first two big families of carbonyl compounds, aldehydes and ketones. Now, these guys are incredibly similar, but there's just one tiny but super important difference in how they're built. And this is the perfect way to see that difference. Just look at the carbonyl carbon, the C in the COO. In an aldehyde, that carbon is bonded to at least one hydrogen atom. That basically means it's always hanging out at the end of a molecule. But in a ketone, it's sandwiched right in between two other carbon groups, putting it somewhere in the middle of the chain. That is the only difference, but believe me, it changes everything about how they behave. So let's talk about aldehydes. These guys are the absolute masters of scent and flavor. Vanillin, that's the molecule that gives vanilla its signature amazing aroma. Cinnamaldehyde, yep, that's the warm, spicy kick in cinnamon. But they're not just about smelling good. They're also industrial workhorses. Think about formaldehyde, which is a key building block for plastics, or acetaldehyde, which is a crucial step on the way to making vinegar. And ketones? They're just as important. Acetone is probably the most famous one. We all know it as nail polish remover, right? It's a fantastic solvent. And then you have others like acetophenone, which provides those sweet floral notes in perfumes. So it's amazing, isn't it? Just that simple change. End of the chain versus the middle of the chain gives these two families completely different jobs in our world. All right, but what happens if we tweak that carbonyl group just a little bit more? Well, you get another profoundly important family of molecules. And that's where carboxylic acids come in. The name actually tells you exactly what it is, which is pretty handy. It's a combo of a carbonyl group, that's our C double bond O, and a hydroxyl group, which is just an OH. And they're both attached to the very same carbon. Put them together, and you get a whole new thing, the carboxyl group, which we write as COOH. So why are they called acids? This explains it perfectly. Okay, first, that little hydrogen on the OH group can pop right off as a proton. When it does, it leaves a negative charge behind. But here is the magic trick. That negative charge doesn't just sit on one of the oxygen atoms. It's actually shared across the entire COO part of the group. It's like a game of hot potato, passed back and forth so fast that neither oxygen really has to hold on to it. This sharing is called resonance, and it makes the whole structure incredibly stable. And because it's so stable after losing the hydrogen, the molecule is more than happy to give it away. And that's exactly what an acid does. And you find these acids all over the place in nature. Formic acid, that's literally the sting in an ant bite. Acetic acid is what gives vinegar its sharp kick. Butyric acid, well, that's the not-so-pleasant smell of butter that's gone bad. And when you get to the really big ones, long-chain carboxylic acids are what we call fatty acids. The essential building blocks for the fats and oils our bodies absolutely need to function.
So when you step back and look at the big picture, the impact of these simple little carbonyl-based molecules is just absolutely immense.
I mean, this really puts it into perspective. In nature, they're responsible for countless scents and flavors. Even our main energy source, glucose, is technically a type of aldehyde. In industry, they are absolutely essential for making everything from plastics to medicines. And in our daily lives? Oh yeah, they are just everywhere, from the vinegar in your salad dressing to the resins in your furniture. And here's the coolest part. For all this incredible diversity and complexity, the basic recipe for aldehydes and ketones is just beautifully simple. For any number of carbon atoms, you have double the number of hydrogen atoms and just one oxygen. It's an amazing testament to how tiny changes in structure can open up a whole world of different properties. So the next time you smell vanilla, or maybe clean something with vinegar, you'll know the secret, right? It's the carbonyl connection. It really makes you wonder, doesn't it? What other incredible chemical secrets are just hiding out in the simple molecules all around us every single day?